Hello again. We are in week 3. What I'll be doing today, we'll actually begin to do real testing algorithms today. So, what we saw till now, we saw various coverage criteria over graphs, structural or control flow coverage criteria, and then we saw data flow coverage criteria. While doing that, we did two things. We considered graphs as just models and defined the coverage criteria, saw what they mean, and also discussed their subsumption relations. And while doing that, I gave you a few examples, but I didn't really tell you how to use these graph based coverage criteria to actually test software artifacts. So, what we will do from today's lecture onwards is to consider software artifacts one after the other and then see how they can be modeled as graphs and how we can use the various graph coverage criteria that we have learned to be able to actually test these software artifacts. The first software artifact that I will begin with is code, source code, because that's the most commonly available source software artifact. In fact, it is the most exhaustive software artifact apart from testing. So we will take source code. We will see how to model it as graphs, and then we will look at one after the other the various coverage criteria that we have learned and see how we are going to apply them to actually test the source code. So when it comes to source code, how are we going to model source code as graphs? The most common model of source code for graph is the control flow graph, right? So control flow graph typically models branching, looping, sequential calls of statements and so on and so forth. It also models things like function calls, class inheritance, and so on. So these are called call graphs or interprocedural call graphs sometimes. And when you club them together along with the control flow graph, you could call it as an interprocedural control flow graph. What we will see today is to take one, assume that the code consists of one method, one procedure, or one function, not several different functions calling each other. We just take this, we'll try to model it, first see how to model it as a control flow graph, and then see how to use the structural coverage criteria that we have learned to be able to test various aspects of this code. In subsequent lectures, I will teach you how to augment this control flow graph with information about data, in particular definition and uses, and how to use the data flow coverage criteria to test these graphs. In between, you might be wondering, I know testing a little bit and I know several common terminologies in testing. So, what we will do is we'll spend one lecture looking at what are the common terminologies that are used when it comes to testing source code and source code with graphs and see how what we are doing relates to what is commonly understood, right? So, what will we be doing today? We will be doing the following. We'll take source code, the code that we are going to test. I'll assume without loss of generality that that code is contained within one method or one procedure. Doesn't have too many procedure calls. We will look at that when we look at design later on. And I'll also assume when I do examples that you're familiar with programming languages like C or Java, right? The basic how to read code. So I'll tell you how to take this code, model this code as a control flow graph, and then how to look at the structural coverage criteria that we defined over this control flow graph abbreviated as CFG. So graph, as we know, has nodes and edges. So what are nodes in the control flow graph modeling a code? Nodes are basically statements or sequences of statements. They are commonly known as basic blocks in the sense that it's one continuous sequence of statements such that there is no branching in between. There is no if, there is no while, there is no for loops. It's just maybe a series of assignments, a series of statements like assignments and printfs, a series of asserts, something like that. It's just a continuous sequence of statements commonly known as basic blocks. And then what are edges? Edges basically dictate transfer of control. So we'll see it through examples in detail. So control flow graphs are many times annotated with what are called branch predicates, which tell you which is the predicate on which you're branching. It comes as labels of the edges. They are also annotated with defs and uses of variables, as we saw in the example. For the purposes of today's lecture, we will look at examples. We look at annotations where branch predicates come. This defs and uses, which deal with augmenting control flow graph with data, I will deal with it separately in another lecture, right? So, what we will do from now on for the next few slides is I'll take each kind of software structure and tell you how the control flow graph corresponding to that software structure looks like, right? So, here is how control flow graph corresponding to an if statement will look like. So let's say we have this code snippet. As I told you, when I show you an example like this, I'm just showing you a fragment of the code. This is not a complete piece of code, definitely not compilable or executable as a standalone entity. We just look at a fragment because our focus is to understand for the concerned fragment how its control flow graph will look like. Later, we'll take a full piece of code, a large example that contains all the statements, and we'll put together the CFGs that we learned to draw for each of these fragments and see how the CFG for the whole code will look like, right? So what I'll do is I'll look at various code structures like branching, looping, exception handling, and so on, and tell you how the CFGs for each of those code structures will look like. So we begin with if statement because that's the simplest. So let's say we had a code fragment that looked like this. So there's a statement which says if x is less than y, then you do these two statements. Assign 0 to y and make x as x plus 1. Else, which means if x is greater than or equal to y, then you say x is y plus 1. And with respect to what you do, when you come out of this if statement, you say z is x plus 1. Right? So how does the CFG for this if statement look like? CFG looks like this. So this node, which is the initial node, what does it say? It corresponds to this if statement. So it checks for this condition. Is x less than y? So suppose x is less than y, then it takes this branch or this edge where it executes these two statements which correspond to these two statements in the code. And suppose not. Suppose x is not less than y, which means x is greater than or equal to y, then it executes this statement, right? It says x is equal to y plus 1. Irrespective of whichever statement it executes, when it comes out of the if loop control flow structure, it executes this assignment statement given here in the graph. Z is x plus 1, right? So here is how a control flow graph or a CFG corresponding to an if statement looks like. So there is a node that corresponds to this check or the if statement. If that check is positive, let's say if x is less than y, then it takes one branch depicted by an edge and executes the statements corresponding to that branch. If this condition is false, then it takes another different branch which represents the negation of that condition. In our case, it is x greater than or equal to y, and it goes to a block where it executes the statements corresponding to the else branch. Whatever it is, it has to come back and merge for this kind of an example and execute the statement that is just outside the statement. In our case, it is z is equal to x plus 1. So I hope this is clear. What we will do is suppose we had just an if statement without an else part. So in this example, we had a then part and an else part explicitly written out. Suppose you just had an if statement which just had a then part, right? I've just removed the else part from the previous example. How does its CFG look like? So as usual, I begin at a node where I check for the truth or falsity of the predicate x less than y. If x is less than y, then I do this. Otherwise, I just exit directly because there's no else part specified. I directly exit and come out to the node that represents the execution of statement that immediately follows the if statement. So now, suppose I had an if statement, but with a specially marked statement called return, right? So let's look at this code fragment here. What it says is that if x is less than y, then you return. And when you return, you print the value of x because that's the statement that is immediately after this. Otherwise, you just return. There's some silly piece of code. Don't worry about what it's meant for and all. Our purpose is to understand how its control flow graph looks like, right? So as always, I start with one node representing this if statement where I check for truth or falsity of this predicate. Let's say it turns out to be true. I come here, take this branch, and then I do a return statement. Suppose it is false, then I come out, do a print x, and then do a return statement. One thing to be noted is that please note that this return is different from this return, right? So this is put by distinguishing two nodes corresponding to the two different returns that are there, one inside the if statement and one outside the if statement. So the next kind of branching that we will be looking at is what is switch case statement. It's another very common branching statement. So let's look at this code fragment. What it says is that you read a value into a variable called C. C looks like a string variable, and then you switch to these different cases based on the value of C. If C happens to be n, the string n, then you execute this statement z is equal to 25. If C happens to be the string y, then you execute these two statements, x is 50 and break. Break means break out of the switch case statement. If it is none of these cases, which means if it is the default case, then you execute these two statements. One of the statements again is a break, which tells you to break out of the switch case statement. Whatever you do, when you come out, let's say you have a printx statement. How does the CFG for this statement look like? So I begin with a node which corresponds to this read C, right? And then I merge it with the same node where the switch C is also taken. I can keep another node which is serially connected to the node corresponding to read C. There will be no big difference. The CFGs are more or less the same. But in this case, I chose to keep one node for both these statements, right? So, and then the next thing represents the three branches corresponding to the three cases of the switch statement. If case is n, I take this branch and do the statement z is 25. If case is y, I take this branch and do these two statements, x is 50 and break. Please read these as labels corresponding to this node, right? They seem to overlap with this edge, but they are labels that annotate this particular vertex. And if if C is not n, if C is not y, then I'm in the default case, in which case I come out and do these two statements, right? And when I break, I go back here, which is the printx statement that is present in this code, right? Now, if you look at the CFG carefully, there is one extra edge here, right? What does that extra edge represent? That extra edge says that the case for n, if you see here, doesn't have a break statement, right? If it doesn't have a break statement, then as per the semantics, the typical semantics of switch statement, I go and evaluate the next case. So what it says is that when it's the case for n, you go ahead and lead it to the case for y and continue from there on. If I don't want this edge, then I explicitly put a break along with z is equal to 25 for the case for n, right? Because such a break is not there, the case for n leads to the case for y as per the semantics of switch statement, and that's the reason why this particular edge exists in the control flow graph. Yeah, now what we will do is we look at loops. When it comes to loops, we all know that there are several kinds of loops. There are while loops, there are for loops, there are do while loops, and so on, right? So to model loops as CFGs, we'll have to typically add a few extra nodes in the CFG. We'll see through examples for each kind of loops how those extra nodes look like and where are they added and what do they represent as far as the loop semantics and execution is concerned, right? So we begin with while loop. Let's say you had a simple while loop that looks like this. You initialize x to 0 and then you say as long as x is less than y, you execute these two statements. You call a function y, you call a function f with the parameters as x and y, and you assign the value that f returns back to y. Then you do this simple assignment statement, which is x is equal to x plus 1. How does the CFG for this code fragment containing a while loop look like, right? So initially, there is this node which begins for this assignment statement, x is equal to 0. Then I come and I have to do this node. So one way of interpreting it is to consider this as a dummy node. Another way of dummy node or an extra node. Another way of interpreting it is to consider node 2 as representing this while. So while this is true, so while this predicate is true, I go to node 3 where I execute the statements that occur inside the while loop, and I go back to checking for the condition in node 2, which means I go back to checking for the truth or falsity of this predicate. When this predicate becomes false, that is when x is greater than or equal to y, I exit out of this loop and I stop. And in this particular code, I haven't really given you what we're doing when it exits the while loop, so there's nothing annotating vertex 4. Right? And vertex 4 is marked as a final state because I stopped there. So is it clear, please? How do while statements look like? They will always have this kind of a branching structure that is represented by nodes 2, 3, and 4. One branch will represent the loop condition or predicate being true, and it will keep looping as long as the predicate is true. That's this branch between 2 and 3. Another branch will represent exiting the loop, that is when the loop predicate becomes false, right? So in the next example, we look at for loop. So here is a very simple for loop. It says for x is equal to 0, as long as x is less than y, x plus plus, you do this condition. Right? So how does this look like? So initially x is equal to 0 is labeled with an initial node. And then here comes this. So node 1 doesn't have explicit status in this code fragment, if you notice, right? So you can think of node 1 as a dummy node that implicitly initializes the loop. Node 2 is the actual check for the predicate x less than y being true. So if it is true, it goes through node 3 where the statement y is equal to f of xy is executed. Now, after this, what happens in the for loop? It has to go ahead and increment x using this x plus plus, right? So I add another node 4, which is actually a dummy node, which implicitly represents x plus plus or x is equal to x plus 1. It goes back after incrementing x, checks whether x is less than y is true. If it is true, comes back, executes this, increments x, goes back, and so on. So this is how the for loop goes on between nodes 2, 3, and 4, and the cycle between 2, 3, 4, and 2, right? So what happens is the predicate is checked, the statements are executed, the variable is incremented, predicate is checked again. That keeps repeating. And when the predicate becomes false, that is when x is less than or equal to y, the CFG exits the for loop and takes this branch and comes to node 5. So is it clear, please, how the CFG for the for loop looks like? So now we'll move on and look at the control flow graph for a do-while loop. So how does a do-while loop work? Unlike a while loop or a while-do loop, do-while loop will execute the statements inside the loop definitely at least once, right? It first executes the statements that come inside the loop. After that, it checks for truth or falsity of the predicate that labels the loop, right? That's what is depicted in this CFG also. So here is a code fragment that has a do-while loop. I begin with initializing x to 0. Then I do the following as long as the predicate x less than y is true. So what do? I do y is equal to f of xy, and then I do x is equal to x plus 1. And when I come out of this do while loop, I do print y, right? So as per the semantics, first these statements are executed, then this condition is checked. So that is exactly replicated in the CFG. I begin with x is equal to 0, which corresponds to this statement. Then I come to a node where these two statements are executed. Y is equal to f of xy, x is equal to x plus 1. That is these two statements. And then I check for this condition x less than y. That is represented as a self loop in this node, because as long as this condition, predicate x less than y, is true, I continue to stay in this node where I execute these statements, right? And when this condition becomes false, I exit and go to a node where I have to actually do print y. I should have labeled this node as print y, right? Because that's where I go to. Please note the difference in the control flow structure for a do while loop and for a for loop and for a while loop. Say for a for loop and while loop, we had this kind of a branching where I first check and branch for truth and falsity of a predicate. I go back in a loop whenever the predicate is true, and I branch out whenever the predicate is false. Same exists for while loop also. I check for the condition in a node. I go back to the node as long as the predicate is true after executing the statements that label the loop, and I branch out and exit the loop when the condition is false. Whereas for a do while loop, I stay at a particular node as long as the condition is true, and I keep executing the statements of that node as long as the condition is true, and I branch out when the condition is false. Right? So the loop sort of in this example is shrunk to a self loop at one node. Now I'll show you a slightly bigger example. Here again it is a while loop, but it has two special kinds of statements. Statements like break and continue, which make loop semantics a little more interesting. So here is a small code segment. So it says start by initializing x to 0. As long as x is less than y, you execute this large while loop. It begins here, ends here, the last but one line, right? What happens inside this while loop? Inside this while loop, I do several things. I first do this y is equal to f of xy by calling the function f, and then I check for two nested if statements, right? So I say if y is equal to 0, then you break. So what is the semantics of this break? This break means where will you come? You'll come here. You'll come to this print y statement, right? And then suppose this is not 0, then you check if y is less than 0. If it's less than 0, then you do something, y is equal to y plus 2, and then you continue. And when you continue implicitly, what are you saying? When you continue means you continue into the while loop. Go back and check for this condition. That's what it's being said, right? So how does the control flow graph for such a code fragment look like? So there is an initial node where x is equal to 0 is given. Node 2 checks for the predicate x less than y. I haven't labeled the edges here to reduce the clutter in the control flow graph. But suppose x is less than y is true, then I take this branch to 3 where I execute the statement y is equal to f of xy. After that, I check if y is equal to 0. If y is equal to 0, then I break. Because I break, I come out and go to the printf statement, which is at node 8. Suppose y is non-zero, then I go here to the else part. In the else part, the first thing that I do is to check if y is less than 0. If y is less than 0, then my code says you do these two statements, y is equal to y into 2, and then you do continue. Continue, as I told you, means that I go back and check the condition of the while loop. Suppose y was not less than 0, y was greater than 0, then I come out of the second if statement and execute this statement x is equal to x plus 1. But please remember, even here I'm within the while loop, so I have to go back through this edge from 7 to 2 to the main condition of the while loop node where the condition is checked, and I repeat the sequence of executions, right? So I hope this makes it clear how the semantics of while combined with if, break, and continue works, and how the control flow graph corresponding to such statements look like, right? Now here is another example of a control flow graph. You might be familiar with this exception handling using try and catch in Java, right? So how does the CFG for such try catch exception handling look like? So here is again a small code fragment which involves a try catch piece of exception handling. So it says there's a try here, there are two catches here. So what it says is that you read the line, assign it to x, right? And you see the length of the line that you have read. If length is greater than 96, then you throw an exception saying it's too long. If length is less than 96, then you check if the length is actually 0. If length is actually 0, then you throw another exception saying too short, right? And if it is too short, then you go back and get the message. If it's too long, then you go and print. If it's not too long, sorry, then you go and print the stack trace. So the control flow graph for such a code fragment looks like this. I begin with reading line and assigning it to S. Then what I do is I come here and check whether what is the length of the statement line that I have just read. If length is greater than 96, then I throw an exception and go out, right, to get another message. Suppose length was less than or equal to 96, then I now check if the length is 0 or not. If the length is 0, then I throw another exception, then I go back to get a message. If the length is non-zero, then I go and return S, right? So this is how the CFG corresponding to a try-catch statement looks like, right? So now what we have done through all the slides that we have looked till now is that I have shown you how to, through examples, how to draw the control flow graph corresponding to several different code constructs. Control flow graphs corresponding to branchings which involve if with then and else, without else, if with return statements, control flow graphs corresponding to switch case statement, control flow graphs corresponding to different kinds of loops, while loop, for loop, do while loop, and CFGs that include while loop with branching and breaks and continues. And finally, in this slide, we saw an example of a control flow graph for exception handling through a statement like try catch. What now, moving on, we will see is I'll show you a full piece of code that does something. We'll draw its full control flow graph, and we will see how to use the various data structural coverage criteria that we have learned to be able to test that source code. So the code that I want to look at is an example of a program that computes the typical basic entities that deal with statistics like median, variance, standard deviation, mean, and so on, right? So what it takes is that it takes an array of numbers and it returns what are the various parameters. So it returns the length of the array, it returns the mean value of the array, it returns the median, it returns the variance, and it also returns the standard deviation. So those are all these println statements. And what does the code do? The code basically has two for loops, one for loop right here and another for loop right here. The first for loop is used to compute median and mean. The second for loop is used to compute the variance and the standard deviation, right? So I'm sorry I put the code in smaller font to make it squeezed into a one slide. This curling closing brackets is sort of gone down, but this represents the full piece of code. It takes an array of numbers. The code is called compute stats and it outputs length, mean, median, variance, and standard deviation. How does it go about doing it? It says the length is an integer variable and the rest of the numbers are all declared as double. It initializes the sum to be 0. Then it goes into a for loop where it repeatedly adds the numbers in the array to itself and computes the sum of all the numbers in this array in this for loop. Then it says median is this, right? Numbers of length by 2, which is the midpoint. And it says mean is sum slash double of length, right? So now this for loop computes the variance sum. So it initializes var sum to 0 and then it gets into this. And what it does is that it computes the var sum as this difference, which is standard way of doing it in statistics. When it comes out, it computes the variance as var sum divided by length of the array minus 1. And standard deviation is the square root of this variance, right? And then it has all these print statements that print the various values, right? Now, what is our goal? Our goal is to take this piece of code and model it as a control flow graph and use the various structural graph coverage criteria that we have learned to be able to actually test this code. So how am I going to model this code as a control flow graph? So initially, when it comes to CFG, please remember we ignore these entities, right? We ignore these statements. So I begin with a node that initializes the sum. That is what is given here as node 1. Then the next thing that is there is this for loop, right? It initializes I to 0, checks for the truth of this predicate, and there is a node that increments I. Whenever this predicate is true, it assigns sum to be this value. So that is represented in this fragment of the CFG. So it initializes nodes 2, 3, 4, and 5 represent the first for loop. So it initializes I to 0. Node 3 is where it checks whether I is still less than length or I is greater than or equal to length. If I is still less than length, it increments I plus plus and adds the thing to sum. If I is greater than length, it goes out here and then enters the next for loop, which is this loop, right? So here again, I check for the same, this thing, and I do this. Just for simplicity and to reduce clutter, I have not labeled this control flow graph fully with all the statements. Like for example, I have not used these two statements. Median is numbers, length by 2, and mean is sum of double length, var sum is 0. Where should they all come? They should all come here as labels of this node, right? But I wanted to focus only on structural graph coverage criteria. So I have just reduced myself to looking at the main CFG corresponding to this one. I have removed all the labels that we are used to annotating the CFG with. I've retained some just to tell you that this little fragment here is for the first for loop. This is for the second for loop, right? Ideally speaking, I should have put all the other labels, but then the CFG would have become too cluttered, and the focus on understanding this example for structural coverage criteria will be lost. So I have just retained as minimal labels as possible. The CFG by no means is complete when it comes to label annotations. So now we've taken this code, modeled it as a graph. Our focus is now purely on this graph, right? We want to now look at this graph, go back, recap all the structural coverage criteria that we have learned till now, and see how we can use some of them to test this graph. So the first coverage criteria that I would like to, you can apply any of the coverage criteria that we have learned till now. We will apply a small sample, 2 or 3 different coverage criteria for the purposes of understanding. So suppose I want to do edge coverage criteria for this graph, right? If you see, I have taken the CFG that was here and further removed all the labels and retained only the core graph. The understanding is that this is the graph that corresponds to that Java code that corresponds to the statistics program. Suppose I want to achieve edge coverage for this graph. What are my test requirements? Test requirement of TR says cover every edge. So this is a set that contains the list of all the edges of this graph. If you see, I have put all the edges in this set 1, 2, 2, 3, 3, 4, 4, 3, and so on. And what is a test path that will meet this test requirement? It's fairly simple, right? I start from 1, I do 2, 3, 4, 3. I have covered these 4 edges. Then I take this branch now, 5, and then I do 6. And now I don't want to do 8, then I would have lost the edges 7, 6, 7, and 7, 6. So from 6 I go to 7, 7 to 6, 6 to 8. That's the path that I have traced out here. I'll just read it out once again for clarity. I go from 1 to 2 to 3 and then move on to 4, come back to 3, come to 5, move to 6, come to 7, come back to 6, and then branch out to 8. So using one long test path that visits from the node 1, which is the initial node, to the node 8, I have managed to achieve the test requirement of edge coverage, right? So this is like a minimalistic test case. Minimalistic because there's only one test path that is enough to test the coverage criteria of edge coverage for this graph. Of course, there's nothing, no harm in you might say that this why one test path? I would write 4 test paths. I would write 2 different test paths. Like for example, I would write 1, 2, 3, 4, 3, 5, 6, 8 as one test path. Which are the edges that are not covered there? These 2 edges. And then you say, fine, I'll write another test path that covers those 2 edges. I could do 1, 2, 3, 5, 6, 7, 6, 8. So my test case requirement of edge coverage is met through 2 test paths. That's also fine. Anything is fine. But idea is the number of test paths we want to achieve for any kind of coverage criteria. Implicitly, we also desire them to be as minimal as possible. In this case, I could achieve it with just one test path, so I just wrote that. But there is nothing that says that this is the only option available. You could do it with test paths that have 2 test paths, 3 test paths. As long as you cover all the edges, we are doing fine. Now, let's say we want to do edge pair coverage for the same statistics program CFG. What is the test requirement for edge pair coverage? The TR for edge pair coverage is this set. I have written it such that I have given a label A, B, C, D, E, and so on for each test case. I will be using these labels in a few later lectures, and I have also grouped them to indicate the edge pair, right? Like for example, 1, 2, 3 is this pair of edges. 2, 3, I could do 4 or I could do 5, so I have listed them together. Similarly, from 3, I could do 3, 4, 3 or 3, 5, 6. So I've listed them together because both begin at 3. Similarly, the ones that begin at 4, I have listed them together. These 2 together and then the rest of them. So this is my TR or test requirement for edge pair coverage, which lists all paths of length 2. Because it subsumes edge coverage and node coverage, I have not listed those paths again. And for this, I will not be able to do it with just one test path. Right? So this one test path is that long test path that we saw before, which is 1, 2, 3, 4, 5, 6, 7, 6, 8. Right? So this test path is needed. What does it miss out? If you notice, which are the edge pairs that it misses out? Does it include, for example, 5, 6, 8? It doesn't, right? Because it doesn't come directly. If you see here, 5, 6, 7 comes, 7, 6, 8 comes. 5, 6, 8 doesn't come. And for now, assume that I don't want to do side trips or detours. So I put another path that includes 5, 6, 8. So I do 1, 2, 3, 5, 6, 8. So that's my second test path. And now we go back here and see what else has this missed. This has missed 4, 3, 4 also. because if you see it's not there here, it's definitely not there here because the path doesn't even come here. It has also missed 767. That's not in both these paths. So I have another test path that includes both of them. So test paths always have to begin at 1, which is an initial node, end at 8, which is a final node. So it's a fairly long path because it has to go through the loop once again. So I do 1, 2, 3, 4, 3, 4. That way I'll include this 4, 3, 4. And similarly for this one also I do 5, 6, 7, 6, 7 so that I can have 7, 6, 7 and then end it with 8. Right? So this is the test requirement or TR for edge pair coverage, and I need minimally 3 test paths to be able to achieve edge pair coverage for this graph. Right? So we look at prime paths coverage. You remember I told you what are the algorithms to enumerate the test requirements for prime paths. So I run that algorithm on this graph, and this is the set of prime paths that I get. If you remember and go back to the slides that we had done then, you would see that I would have taken the same example graph and we would have worked out the prime paths as these, right? So I'm just taking it. It so happens that this is the graph that comes as the CFG for the statistics program. But these are the set of prime paths, so that's my TR. And for meeting this TR, I need 5 different test paths, right? So this is how I do prime pair coverage. If you see, they examine these 5 different test paths, they will neatly execute the loop. There are 2 loops in the graph, one for loop here and one for loop here. Between these, they will neatly skip the loop and execute the loop each in turn for both the for loops. And so I achieve loop coverage implicitly for prime path coverage for this program. So what did we do in this module? We looked at how to draw control flow graphs corresponding to source code and how to apply elementary structural graph coverage criteria to test the control flow graph, in turn the source code, by using these criteria. The next lecture will continue with source code. I will tell you what are the classical notions of testing related to source code and how do they relate to the structural coverage criteria that we have seen so far. Thank you.